Civil Handbook.
All right. Let's get started. Now that most of us are done with our lab exercise for the week, and we can all forget about me mixing up formulas between flatness and elongation. So I swear I was like, what are you talking about? And I was like, oh, I know what you're talking about. I made a boo-boo. That's what I'm... So I'll talk about that tomorrow in materials, but I had a slight typo on one of my formulas for the lab exercise, and yeah, that created some confusion. So, but that was on me, so that won't be held against anybody in 321. Okay, I'm a little behind on homework grading, I won't lie. So that's going to be sort of a now like we had our weekend, and then we came back, and I was spent all day getting ready for labs, so I'm a little behind on homework grading, I won't lie. So my goal is probably sometime, I would like to think today, but it might be tomorrow, but I'm just going to try and knock out homework 2.2 and 2.3 just all at once. I also know that there's like a couple attendance things I need to correct. I'll do that between now and Friday. So when we come back, hopefully everything's up to date. So I mean, the attendance grades are up to date on Blackboard for most of you, but I think there was a student or two who might have missed the QR code, which, by the way, if you have not done it, it's right here. Make sure and scan it. So, okay. How did the frame homework go? I am curious. The cutting the section with the weird loads and all that, was that good? Okay. Hopefully you found that when you just sum, like you could sum moments at one support to get the vertical reaction, and some horizontal or some verticals, like you should be able to compute the vertical reactions without having to cut a section. And then it's cutting the section would give you the one horizontal reaction, and then summing forces in the x direction gives you the other. That's probably the most straightforward way to do it. But beyond that, that is the end of reactions in here. When I say it's the end of reactions, I mean that it's the end of specific coverage of reactions. This is a structural analysis course, and there is pretty much no way to ignore the computation of support reactions for the rest of the semester. But moving forward, I'm going to be giving you problems where I might already give you the reactions, or if it makes sense to compute them on board, I'll do it. But I'm going to sort of assume that we're all good with the computation of support reactions. So before we open up the land of trusses, is everybody good with support reactions? Is there any like high level or detail oriented questions you want to ask about reactions, or is that a topic that we can all assume we're good with moving forward? We're good? I'm seeing some head shakes and some thumbs ups. Okay, so we can talk about trusses. Okay, everybody get the code? All right. Let's talk about trusses. All right. Okay. So everybody in here, I think, has done a truss analysis before. And a lot of what we do in the first part of this class is sort of a little bit of a repeat of what you've probably seen in statics, but we go a little bit more in depth, and the structures that we assess are much more tricky and much more complicated. But this is stuff that you probably have seen before. So what we're going to do is we're going to talk about trusses. We're specifically talking about their behavior, and we're going to discuss the method of joints. When you take a statics course, really trusses are something that you cover at the very end usually. Like you spend most of the time discussing like what is a force, what is a moment, and then at the very end of the class you go, okay, here's some applications. And so you talk about trusses, but it's really high level, and the trusses that you do in there are really easy. And then you get in here and it's like, okay, we gotta do some real truss analysis in here. The other thing is that it's really advantageous to cover this, because one thing you didn't cover in statics was truss deflections, and you do need to be able to solve a truss in order to assess truss deflections. So that's what we're going to talk about in here. Now, I went forward one more slide than I wanted it to. There we go. So let's talk about trusses, though, before we go too far down the rabbit hole. Let's talk about trusses in the context of civil engineering. I mean, first off, hopefully we all know what a truss is. It's just a triangular arrangement of members, or members of members in triangular patterns. Characteristics of trusses is that the members are straight, they're not curved or arched, and that they are arranged, like I said, in some sort of triangular pattern or triangular network. Trusses themselves can either be a component of a structure or they could just be the structure, okay? Examples of a component of a structure would be like a roof, right? It's very common for trusses to be roof elements, mainly because they allow for easy drainage of the water or snow on top of the roof. They also are very nice as options for bridges, okay? The thing about trusses for bridges, though, is that from an economy standpoint, trusses usually are only economical when you have relatively long spans, okay? For short spans, you're not really going to see a lot of trusses constructed because we can just handle that with beams or a beam and slab, or honestly just a solid slab system if it's really short, or maybe a culvert or whatnot. We don't really need trusses for until the spans get really long. Now the thing about trusses is that trusses, when you compare them to, let's say, beams, like their counterpart, trusses tend to be much more lightweight. They tend, like if we were to pick up that truss on the right with a crane, it would weigh less than its comparable beam counterpart in order to achieve the same stiffness. And that's the other thing about trusses. Trusses are structures that have a relatively high stiffness characteristic. Now, I'm using the term stiffness specifically because stiffness is not the same thing as strength. Okay? Those are two different terms in structural engineering. Strength is how much force an element or a system can withstand before it fails. Okay? So in other words, strength would be if I had this marker in my hand, how much force until I literally snap the marker in half. That's its strength. Okay? Stiffness is the relationship between applied forces and resulting deformations. Okay? And they aren't the same thing. Is there a relationship between the two? Yes, but they're not the same thing. The stiffness would be, so for example, imagine I had two springs in my hand, and I took the springs and I stretched them with a force of, let's say, 10 pounds, okay? Stiffness would be, if I put 10 pounds on spring A versus 10 pounds on spring B, how much does spring A versus spring B stretch? Like if spring B stretches more than spring A under the same load, then spring B is not as stiff, okay? Even if neither of them break under 10 pounds. Does that make sense? So that's the difference between strength and stiffness. And trusses are incredibly stiff systems, okay? So yeah. All right, let's talk about trusses, though, as structures as they relate to our mathematical modeling. Remember, we do not analyze structures as much as we analyze mathematical models that represent them, okay? So we make a series of assumptions when we analyze a truss, and we make three basic assumptions, but these three basic assumptions are really focused on trying to achieve a given result. We'll talk about that result here in a second, okay? But let's go through them each one at a time. Okay, so assumption number one is we assume that all of the members are connected by frictionless joints. Now, is that assumption 100% true in the real world? No. Friction always exists when two surfaces are in contact, so I mean, we can talk about the degree of that, but what is this assumption trying to get at? Essentially, what it's trying to get at is that there's no forces in the system other than what you can see directly from the model. In other words, you know, you've got member A connected to member B, and they're loaded, but there's not also some friction between two components that we need to account for. We can sort of ignore that for the purposes of analysis. So it's basically trying to say that what's on the model is really what you need to account for, and that's it. Okay. What about assumption number two? Assumption number 2 and 3 are very related, even though it might not seem like it. Assumption number 2 says that all the loads and all the support reactions are applied at the joints. Okay? So, for example, I have a truss here on the board. You will never see us do a truss analysis in this class with a load like this. Okay? You don't see that. You only see concentrated forces at the nodes, N-O-D-E, the nodes where the members intersect. So if you ever hear me use the term node and joint interchangeably, they essentially mean the same thing. Okay? So where the joints are where the loads are applied. But assumption number 3, this one actually has probably the most physical meaning as well, and that's that at each joint, the centroidal axes of each member coincide. So let's go back to statics. Remember the centroid, right? So if I have a cross-section, like a shape, I can compute that little point that we call the centroid, sort of like the middle, if you will, of a shape. I propose that if we look at the centroid, let's say of this top chord, this vertical member, this top chord, this diagonal, etc., that they all meet at a common point, okay? And we can actually engineer that when we fabricate the truss, and we do that in the real world, okay? What we're doing with these two assumptions together is we're basically saying that there is no shearing and there is no bending of truss elements. In other words, we're not taking the element and we're not bending it. We're not taking the element and we're not shearing it. The only thing that the elements are experiencing in a truss is an axial force. It is either being stretched or being squished, okay? And we do that by saying all the centroids all meet at a common point, and all the forces that are applied to the truss go through those points. And that's what I meant when I said these two are related, okay? So what these two are saying, these assumptions 2 and 3, are saying all the members meet at common points and all the forces are applied to those points. And then assumption 1 is basically saying those are the only forces you need to consider. You don't need to consider any friction or anything else going on in the system, okay? So it is from these 3 assumptions that we can idealize trusses as only carrying axial forces, okay? So in other words, if I have an arbitrary structure and some random frame or beam or whatever, and I take the samurai sword or a lightsaber through that system, at any arbitrary point in an arbitrary structure, I might get 3 unknowns. I might get an unknown axial force, an unknown shear, and an unknown moment. But a truss is a special system, okay? Because of the assumptions that are baked into the truss, and coupled with that, the ways in which I fabricate the system, I can assume that instead of having an axial force, a shear, and a moment, I only have an axial force. And the question is that axial force in tension, or is that axial force in compression, okay? So instead of there being 3 potential unknowns for each member, there's only 1, okay? So this could be 20 kips in tension, it could be 30 kips in compression, it could be 0. And we will talk about zero force members a little bit later. I think probably on Monday we'll talk about zero force members, okay? Okay, does that make sense? Okay, now, has it been a while since you looked at this stuff? Been a while, right? Then this is an apt discussion. Okay, let's go back to the wonderful world of statics, and let's have ourselves a collective discussion about ENGR 213. Okay, so the very first thing that you discuss in statics after you do, your intro review and all that jazz, is you discuss a concurrent force system, otherwise called a particle statics problem. Y'all remember that? So like you'd have a problem where, you'd have, I don't know, like let's see if this problem rings a bell in statics. You have like a floor, you have an eye bolt, right? Then you have a rope going this way, a rope going that way, rope going this way, rope going that way, all through that point. And the question is, what's the resultant? Y'all remember that? Very fundamental problem in statics. Right? What is the resultant? Okay? Now, when you first take statics, this is like one of the first classes of problems that you deal with are the particle statics problems. And if you remember, let's go back to statics. Does anybody remember, how do you solve this problem? So this is F1, F2, F3, F4. Does anybody remember how do you go about solving this problem? How you did it in 213?
Do you put every force in the XY components?
IJ notation, right? So we'll take this one and we'll say something times I plus something times J, something times I plus something times J, right? And do the same thing for all of them, and then add up all the I components, add up all the J components, there's your resultant, right? And if you want to get the magnitude of that resultant, just break out your old friend, the Pythagorean theorem, sum of x squared plus sum of y squared, take the square root, there's your resultant, right? Did I, okay, so is that how you do this problem, right? Did I, in this problem, mention the word moment? Do you need moments to solve this problem? No, you don't, right? Why not? Why did moments not show up in this problem at all? Okay? The reason why is because all the forces go through a common point, right? When all the forces all go through a common point, there are no moments. Moments are when you have a point here and you have a force that is separated by some line of action, right? Okay? And so in the land of statics, we call that maybe either a concurrent force system, where all the forces meet through a common point, or a non-concurrent force system, where forces don't meet through a common point. Remember that? Okay. If you remember that, then I think that serves as a nice little backstop for why we develop the two methods for truss analysis the way that we do. Remember, in a truss, we have several assumptions baked into the background. Okay? Those assumptions essentially mean that the members only carry axial force. So let's talk about the method of joints. The method of joints is a structural analysis method where all of the forces, where we investigate the equilibrium of each joint one at a time. And if we look at each joint one at a time, each joint one at a time is a lot like this problem. Okay? And if it's a lot like this problem, then there are no moments. Okay? This is a concurrent force system. Okay? Now, there are some limitations to doing a method of joints problem, which we'll see here in a second. But what I'll say for the purposes of a truss analysis is that the method of joints is a tedious method, but it is thorough. Okay? In other words, if you apply the method of joints for a structure, you will solve the entire structure. Okay? Takes a while, but it'll work. What about the method of sections? Well, the method of sections involves taking the samurai sword or lightsaber and cutting through the element, and now we have a concurrent, or a non-concurrent force system when we look at the method of sections. Okay? Now, from a strategy standpoint, what I'll say about the method of sections is that the downside is that it doesn't work very well for solving the entire structure, but if you're trying to find the force in, let's say, this member, it's a lot faster than solving 4 or 5 joints than it is just cutting a section. Okay? In this class, I spend 3 lectures on the method of joints, 1 lecture on the method of sections. And the reason for that is the method of joints does get you the force in every element in the structure. And more often than not, we're civil engineers, we're structural engineers, we need the force in every member because we got to design the truss. Getting the force in a member doesn't really help us very much. It's nice for things like the FE exam and spot checking, and sometimes it's necessary to cut a section for particular trusses, but more often than not, the method of joints is what we want to be very familiar with. So let's talk about the method of joints. That's what we're going to talk about today. Now, the method of joints is an assessment of concurrent force systems. As a result, we do not have the ability to apply the sum of moments because there are none. At each joint, all the forces meet at a common point. Okay? So what does that mean for you as the analyst? Whenever you assess a joint and you're trying to assess the equilibrium of a joint, you can only assess a joint that has at most 2 unknowns. Why? Because you only have 2 equations of equilibrium. You don't have 3, okay? Because all the forces all meet at a common point, there are no moments. So you have to be a little bit strategic when you utilize the method of joints. And I'm going to go through that strategy with you in the example we're about to do today to sort of explain how you should plan out doing a truss problem. And so we're going to sort of do it on the fly with today's example, but on Friday's example, we're going to plan it out at the very beginning. Because I find that if you take a minute and plan out how you're going to do a truss analysis, it will make the flow of that problem so much smoother instead of just diving headfirst into a problem without having a plan of how to get out. Okay? Does that make sense? Let's see what I mean when we go through this example. Okay. Let me pull this up on the notebook here. Okay. All right. So here's a truss problem. Okay. So what we're going to do is we're going to determine the internal forces in this truss. We're going to solve the truss. Okay. Now, a couple things about this truss that I want to clearly point out. First off, I have given you the support reactions. Okay. I'm giving you the support reactions because I think at this point you all should know how to compute them. Is that an okay assumption at this point? We've already had 4 lectures on it. I mean, think, I've got 15 kips going to the right, I got 15 kips going to the left. You know, I've got 10, 20, I got 30 down, I got 30 up, you know. And I could just some moments here to get that one, some verticals to get that. So, I mean, I'm hoping that, like, me giving you those reactions is just sort of a pretty straightforward. Is everybody good with that? Okay, so that's point 1. Point 2, okay, I've made a specific decision with this example that all of the diagonals are oriented at a 3 to 4 slope ratio. So every one of these diagonals is at a 3 to 4 slope ratio, and I'm doing that on purpose for this one. Because the thing about truss analyses is that truss analyses are bookkeeping challenges just as much as they are computational ones, and I'm trying to soften that part a little bit. So I don't want you to have to worry about different members having different slope ratios yet. We will do that on Friday, but today we're going to assume that they're all the same. Okay. Third point. This truss, so like I said, I want to make the bookkeeping a little bit easy, but I'm not going to make it too easy. This truss is not symmetric, okay? And let me be clear. It is symmetric geometrically in terms of the geometry. In other words, I could take the truss, fold it in half this way, and I get the same truss one way as I do the other. But it's not symmetric with respect to the loads, okay? I've got this load going down, this load going down. I don't have like a 10 kip here, and I've only got that there. The loads aren't symmetric, okay? If your truss is symmetric with respect to both geometry and loading, you can get by with only analyzing half the truss. I'm not doing that today, because I do want to stretch our bookkeeping skills a little bit to make sure that we're comfortable with a full-fledged truss analysis. Okay. Sound good? Okay. So let's begin with our method of joints analysis. Now, as I said, we're going to investigate the equilibrium of each joint one by one, okay? And investigating the equilibrium of each joint means we can only select a joint that has, at most, 2 unknowns. So a question for the class, could I analyze joint B right now? No. Why can I not analyze joint B? How many unknown forces are going through joint B? 4, because I've got this member, this member, this member, and this member. That is not to say I can't analyze joint B at all during this problem. I just can't analyze it right now, okay? Which 2 joints could I start with right now?
A and C.
A and C, right? Okay? So what I'm going to do here on the board is I'm going to make a little order list. What order in which I'm going to solve these joints. Okay? For this problem today, we're going to do this order as we go. Okay? But on Friday, we're going to do the order right at the beginning. We're going to make a plan and we're just going to go with it. Okay? And that'll become clear how we do that after today's lecture. So I'm kind of a left to right kind of guy. So I'm going to start off with joint A. Okay? So let's look at joint A. Now I've got this written here on the board, so that way, you know, me scrolling up and down, I can sort of eliminate that a little bit. Bless you. All right, so let's look at joint A. Okay. All right. So I tend to do these in order. So the first thing I'm going to do is draw the members going through joint A. About like that. So those are the members going through joint A, that and that, just these members. So essentially when I do an equilibrium analysis of a joint, again, I'm just looking at this joint. Okay? Next thing I'm going to do, if I have a diagonal member, I'm going to indicate that slope ratio right there. So like step 1, draw the members. Step 2, indicate the slope ratios for any of our diagonals. Okay. So step 3, maybe I'll write those down. So step 1, members. 2, slope ratios. Step 3, known forces. Okay, so what forces are known that are passing through joint A? How many forces do I know that are passing through joint A? 2. This one and that one. So let's just write those down. Okay, so this vertical one, and that one's 15. Okay. And so step 1, our members, step 2, our slope ratios, our known forces, and then our unknowns. Okay. So when I put my my unknowns, what I like to do is I'll say, okay, let's mark this one like that. We'll call that AB. And I'm calling it AB because it's from A to B. And then this diagonal. Okay, for this diagonal, I like to split that up into X and Y components. ADX and ADY. Okay. Does that sound good? Okay. Part of the issue with a joint analysis is really just making sure that you account for everything. One of the biggest mistakes you can make on one of these problems is forgetting something. Like, oh, I forgot the 15, or I forgot the 12 and a half. So be a little bit systematic when you draw them out, because again, that's one of the biggest challenges. Okay. Now, let's go through our unknowns. Okay? How many horizontal unknowns do you see present on this joint?
Just one.
Horizontal.
Oh, sorry. 2.
2. I see this one and this one. How many vertical unknowns do you see? What's that? 1. Okay. So, should I handle my sum of forces in the y direction first? Right? I mean, if I sum forces in the y direction first, what does that tell me? What is ADY?
12.5 kips down.
There we go. Okay. All right. Now, one little note before we start going too far down this. Okay. Okay, so if I have a force that goes along an axis, that force could either go up or it could go down, right? Like if I'm talking about a diagonal path, it could either go up or it could go down. Now, if I split that up into x and y components, it's either going to go up and over or down and in, okay? So what I'm saying is whenever we're talking about axial forces, okay, are we saying that goes down? We're saying ADY goes down because we just figured that out. If ADY goes down, that means ADX has to go in. In other words, like these are correct. This is correct. Having this go down, this go like that, that's wrong. You can't have that. Okay? They either both point towards the joint or they both point away from the joint. Does that make sense? They can't, because at the end of the day, those are components of a force that are acting along this axis. It either points to the joint or away from the joint. Make sense? Okay. Because that's all we're doing. We're taking these and splitting them up into x and y components. Okay. Move this over here. Okay. Now, I want you to get in the habit, whenever you get the vertical component of a given diagonal, to get the horizontal component, or vice versa. And the way that we're going to do that is with the slope ratio. Now, how are we going to do that? It's really easy. Okay? I propose that ADX is to 3 as ADY is to 4. So therefore, how do we solve for ADX? We multiply both sides by 3, and we get ADY. Okay? It's a pretty straightforward calculation. The one thing you want to think about is, if we look at the horizontal and vertical components, the horizontal is smaller than the vertical, so this horizontal component better be smaller than the vertical. In other words, it can either be 3/4 or 4/3. And it's got to be 3/4 because the horizontal's got to be smaller. Okay? So what do we get for this? Because everybody brought the Casio FX115 ES Plus or similar sign to the calculator to CE312 structural analysis.
9.375.
9.375. And that is going to go like that.
And that one goes to, oh, that's ADX.
That's ADX,
I'm
yeah.
looking at AB.
Okay, let's talk about AB. All right. So now how many unknowns do we have now? 1, which is AB. And we're going to solve for that by summing forces in the x direction. So let me move this down a little bit. So, do we need to draw the table, or can everybody, do you think you can eyeball this? I think we've got 15 kips going to the left. We've got ADX going to the left. We know what ADX is. How much do we have to have going to the right in order to maintain equilibrium?
24.375.
24.375. Do I have a second? I think we can all see that one, but does that sound good? Everybody good? Okay. Now, before we finish a joint analysis, I want to see if we can summarize our results, okay? Because at the end of the day, what matters is magnitude and essentially our sense, okay? So let's talk about force AB, okay? Force AB, we ultimately found was going this way, okay? Now, if you recall from truss analysis, a force in a truss member can either be in tension or compression, okay? Now, the way that we figure that out is we look at the joint and we ask ourselves, is the force going away from the joint or is it pushing towards the joint? In the case of AB, the force is going away from the joint. So is that yanking on the joint or squishing on the joint? Yanking on it. So is that tension or compression?
Tension.
Tension, there we go. So this is going to be 24.375 kips in tension. Now, how much force is in member AD? How do I figure that out?
Pythagorean theorem.
Pythagorean theorem. So that's going to be and that's going to be what?
16.625.
16.625 kips. Now, in what? Tension or compression?
I got 15. No,
Is that what I said? 15.625?
you said 16, but I said 15.
Oh, I meant this. Is that what you got?
Yes.
Okay. Maybe I had a tongue slip. All right. Is that tension or compression?
Compression.
It's compression because both of those arrows are facing towards the joint. Okay. All right. Before we go down the rabbit hole any further, I really want to make sure that this first joint that we've analyzed together really makes sense. If there's anything about this joint that didn't make sense, please, raise your hand now, because we're just going to keep going on and doing this over and over and over again. So if this first one didn't make sense, then the rest are going to be that much more challenging. Okay? Everybody good with this? All right. Now here on the board, I'm going to say wait, nope, I got that backwards. I got that way backwards. So this is 24. So I'm sort of writing the answer right there on the truss member, okay? Everybody okay with that? Now, the other thing I'm just going to do right now is I'm just going to sort of indicate we've got this member figured out. We've got this member figured out. So now what? Now what we need to do is we need to pick another joint and press on. Can we do joint B? I really want to analyze joint B. Can we do joint B?
No.
No. Why not?
There's 3 unknowns.
There's 3 unknowns. That means I can analyze joint E, right?
No.
No. But what joint can I analyze?
C or D.
I could do C or I could do D. Now let's look forward in the future a little bit. When I solve joint D, what is that going to give me? It's going to give me this member. It's going to give me this member. Could I analyze joint B then? Right? Because what will happen after joint D? I'll know this one and know this one. That'll leave these two. That means I can analyze joint B. So that'll give me this one and this one. And then what's left? Well, I could do C or E, right? Would it really matter which one? Wouldn't, right? Now, I'm lazy when I do these problems. I'm a lazy analyst. I will never deny that. So I'm looking at joint E, and I've got 1, 2, 3 members framing into it. Joint C has 1, 2 members framing into it. I'm going to do the one that has less bookkeeping, so I'm going to do that one. Okay? So notice what I've done is I've said, okay, if I do joint A, then I do joint D, then I do joint B, then I do joint C, the truss is solved. This is what I meant when I said plan it out. Plan out the order. And let's plan out the order before we do the problem. Now, we kind of didn't really do that with this one because we're just getting back into the swing of things. But on Friday, we're going to do that. Okay? Sound good? All right. So let's go through and do our next joint. Okay? And we might not finish this example today, but that's okay because what really matters is just making sure we understand the method. Okay, so let's do joint D. Ooh, okay. So, what's the deal with joint D? Okay, so again, remember, this is an unknown. This is an unknown. So, what do we know with joint D? We know, let's go to our order. So, step 1, we draw the members. Let's draw our slope ratios. Okay. Now let's draw our knowns. Okay, and this is probably the last bookkeeping thing that's a challenge. Okay. Are there any loads on top of or on this joint that we need to account for? The 10 kips, right? So we have a 10 kip load going down. Okay. What about internal forces? Do we know any of the internal forces? We know this one, don't we? Didn't we just solve that? The X and Y components, I believe, were... Come on. Why? I don't want the arrow. Let's just leave it like that. Okay, so this is 9.375 kips, and this is 12.5. Okay, the hardest thing probably to make sure you're familiar with as your bookkeeping is the arrow direction. Okay, now I propose for these arrows that they need to face this way and this way. Okay? Now that is opposite to what we found out before. For example, I've got the 9.375 going to the right, but up here I had 9.375 going to the left. What gives? Why are they opposite? Okay? Here's a marker. I want to take this marker and I want to squish it. I want to put it in compression. I'm going to take this hand, I'm going to push it that way. This hand, I'm going to push it that way. So I'm going to press my hands in opposite directions. One hand's going one way, one hand's going the other way. If I want to yank it in tension, yank, yank. Opposite, right? I'm looking at the other joint, okay? What I'm saying is on joint A, the forces went into the joint. On joint D, the forces go into the joint at equal and opposite directions. Does that make sense? That's what I'm getting at there. Okay. Okay. List my unknowns, my horizontal and vertical right here, my horizontal there because it's just a horizontal member, and I've got my truss over here where this is DE, that's BD, so we'll just do X and Y. So what equation of equilibrium should I use first?
Some of the forces in the X direction.
X or Y?
Probably Y.
Yeah, because we've got two unknowns in the X, one in the Y. Okay, so let's see if we can do this bookkeeping. Does anybody know what BDY is going to be?
2.5 kips down.
There we go. Okay, so because this is going up 12.5, this is going down 10, we need another 2.5 going down. So if this is going down, let's see if we're all paying attention. Which direction is BDX going to go?
Right.
To the right. And how can we figure out BDX? There we go. Okay. And so that's just going to be the same thing we did before, 3/4 of BDY. And so what's 3/4 of 2.5? What is that? 1.875? To the right. And then now I just sum forces in the x direction. And what do I have? I have 9.375 going to the right, 1.875 going to the right. So I need DE to go to the left, don't I? And DE is going to be what? 9.375 plus this. So 11.25. Right? So, I mean, what do I have? Okay. We're running short on time, so I'm going to run through the math here on this. So, Pythagorean theorem on this is going to get you 3.125 kips. And is that tension or compression for BD? Tension. And then DE is compression. Everybody kind of get the gist of what we're doing here? Everybody kind of get the gist? Pretty straightforward, right? So, here's what I'm going to do because we're running short on time. If you want to continue this problem, what I'm going to do is I'm just going to give you the remaining results. So, I can tell you that BE is 21.875 in tension. I'm going to give you BC, which is 13.125 kips in tension, and CE is 21.875 in compression. Okay. Does that make sense? All right. The other thing I'm going to tell you is I'm giving you a homework problem today where it's a truss analysis. What I would like for your final answer is for your final answer to look sort of something like this. Like you don't have to do the little squiggles, but I'm saying like a final answer with all the forces on the truss. Just member force, so that it's all graphically there. That truss is very much like this one in the sense that all the members have the same slope ratio. They're all, the loads are pretty straightforward. I actually think I'm going to say it, I think it's maybe a little bit easier than this one. The only thing is that the truss goes up like it's sort of like it looks like this. So the truss looks like that, and so there's like that, I think it's like this, I think it goes like that, something like that. So, I think it's probably the same number of members, so. Okay, does that sound good? I'm gonna pull the code up one more time, everybody, but I'll see you on Friday. We'll talk about internal indeterminacy on Friday, too. Oh, yeah, that's right, you'll see me tomorrow.